We're here to talk about fish, and the Council's historic methods of estimating the fish habitat requirements in a stream, and then consequently how much water is available for allocation, and how that thinking has evolved over time. And we've evolved that thinking with the Cawthron Institute and NIWA. So predominantly John Hayes and his team, who have developed a bioenergetics fish habitat model. Karen Shearer has done a fair bit of the grunt work counting invertebrates and putting them into size classes. Eric Goodwin is the computer coding gaming guru that's pretty much put this fish computer game together, and Joe Hay for his inputs too. But we've got a big hydraulic modelling team, Fish and Game, and Environment Southlands field team is too numerous to mention for this work. I'm going to just whiz over the allocation method at a pretty high level just to give you a feel for what it is, and how that may or may not have represented the feeding or habitat space requirements of fish, and then, given the new findings, what the implications might be for water resource allocation. So we're in a situation of high demand, or high allocation, and then increasing demand. And in terms of resilience, it's not going to get any better. So how do we take into account our in-stream requirements for the future? So we want a really robust method to do that. It's not fair to say that the Council hasn't been using a robust way. We have been using traditionally the best way available, and that's river habitat simulation modelling, RIHAB-SIM. And that takes the physical parameters of a river, so depth and substrate and velocity, and relates that to counted fish to develop these habitat suitability curves. So basically where there's colour, it's more suitable given a certain parameter. And there's our river channel. And it doesn't necessarily put those fish in the right spot. When you combine our flow and our depth and our velocities and cross sections of the river reach, we're able to aggregate those into a curve, and that's the habitat method, so the green line here. Around that we've built in management flows, and traditionally that's been around the mean annual low flow, and we allocate 30% of that mean annual low flow as an envelope on top of our management flows. By way of example are just some very rule of thumb methods, and they were developed basically by saying bigger rivers have more fish, more water, more fish. So that's the historic flow method. We're able to allocate a percentage of the flow through the flow range. We shouldn't see a difference in the fish ecology. But it's very rule of thumb. So we tried to, we developed our last water plan, employ the RIHAB-SIM method to try and give us the most robust work available. But yeah, there's that high degree of uncertainty. So for fisheries with high value, we need to include the invertebrate supply. And there are two aspects that control that. One is the benthic invertebrate habitat, so substrate and its distribution. And that's the sort of the paddock size and quality for fish to live in. And that's an expression of, I guess, the life supporting capacity of a river. And then there's the drift transport capacity. And that's the fundamental process of rivers to entrain invertebrates from that habitat into the flow column. And that drift transport capacity is sort of a tangible expression of the Māori of a river, so the ability of it to provide life and health. We undertook net rate of energetic intake modelling, bioenergetics modelling on 3 reaches across 3 catchments. And today I'll present results from the Mataura and some initial results from the Ariti. We're leaders in the country for applying this method, and in terms of the density of the studies, we would be up there in the world with the work that's coming out of Southland in relation to fish requirements for flow. So the Mataura at Otameter and the Ariti at Branksholm aporeminate raised bush. These reaches were chosen for their geomorphology, really. We needed a representative reach that had enough pools and riffles and runs and other habitat, plus the ability to measure those flows to develop a flow rating to run the model through. Because it's not easy to be able to predict how an invertebrate might get entrained and then how a fish might be able to access that to be able to then sustain itself in the river. So we collected heaps of data. We developed digital elevation models from photogrammetric methods, so using drones, manned and unmanned boats for bathymetry, total station surveys, high precision GPS, characterized sediment distribution from the photogrammetry, and also just going out and marking it down on a sheet where we couldn't get any visual data. To create that playing field, to create that ballpark of where invertebrates might live and how they might respond to changes in flows. A key part of that was developing the relationship of invertebrate entrainment with flow. So to do that, we put out nets into the river channel, and over the recession of the river, captured the density of entrainment as the recession went down. Eric Goodwin got tricky with some 3D geometry and understanding of where the bioenergetic requirements of the fish. So where can it efficiently live and then efficiently feed, rest and feeding habitat. And because we've collected all of that terrain data and all of the flow data, and we've modelled it at a really high resolution, we're able to start placing trout into the river in response to the energetic requirements of the fish and other drift feeding. Well, we did it for trout. The greatest body of work in this area has been on trout, and it's our sort of apex species. But the results that come out of it will hold true for other drift feeding fish. Here we have, profitability maps or contours. So where it is energetically profitable for fish to feed at different flows. And if you look closely, you can see black dots, and those are fish. So we're actually predicting the fish count in a river. And here we've done it at 15 and 25 QMEX. So that's at the mean annual low flow of the Mataura, plus at that sort of halfway to mean flow level, where we have traditionally been allocating our water, where the greatest demand is on allocated water, river flow. A nice map's always good, but how do we trust these data? And we can see in this map on the left, the chart on the left, we have measured invertebrate drift concentrations and predicted drift concentrations. So we can see that the predicted drift concentrations match very closely with the measured at a range of flows. So that's really interesting. We can start to trust how our invertebrates are being entrained and how the fish might access them. And this graph on the right here is really interesting. There's results from the Mataura and Oriti studies. So the Mataura is the red line, the Oriti is the blue, and it's showing that the response of drift concentration to flow is consistent between the two rivers, so we've applied the method well. And it also shows that there's potential high level of sensitivity to drift and flow concentration. So if the concentration of invertebrates drops, then the fish have to work more to find the invertebrates that are in there. So a small change in the drift concentration can have a larger effect on fish population. So the drift rate, or the flux of invertebrates, is concentration times velocity, and that basically equals how many fish. And so on the left, we see the results. This is from a comparative paper that Hayes and Goodwin published in 2016 from the Mataura results. Basically, on the left is our traditional habitat method, and we see declining or asymptotic response of invertebrate to flow. Fish habitat to flow. It's the score on the right there. And on the left, we see the net rate of energetic intake results, where we can predict the number of trout and their response to flow. And the key thing to take away is that using a biologically realistic method produces a biologically realistic result. And that result shows that the water that we have allocated at the period we've allocated it in the hydrograph is far more important than previously estimated using our current allocation. The importance of that and the effect on fisheries is now being investigated. So we've got a robust, realistic basis to make decisions on water allocation and that gradient between in-stream and out-of-stream uses. We also have defined an environmental gradient that is the expression of life supporting capacity, which is something that has been missing when we come to talk about values. And that the traditional Raihabson methods might underestimate the feeding requirements.